Okay, so welcome back. Um, Reminders for those working ahead, homework B1 is available, lab 2 is available. This week is lab 1 though. So some of you already turned in lab 1, thanks for that. Lab or lecture unit B is going to be over chapter 2. So if you're reading ahead in the textbook, it's now a good time to start taking a look at chapter 2. ICA B2, remember that's due before lecture B2, so that's before I think Thursday of next week. It is available. It just has 5 questions, covers some basic simulation concepts up through chapter 3. So we're been working through chapters 2 and 3 in the book. So that's kind of what's coming up here. Any questions about any of the assignments so far? All right, so with that in mind, so we talked about modeling before, and now we're going to move into simulation modeling today. And so as a recap, last time we talked about how we have to develop models because as industrial and systems engineers, as operations researchers, then we don't really have a science to lean on. We're dealing with systems for which there often is no knowledge that is already out there provided from another discipline. And so we have to build that knowledge ourselves, these complex mixtures of humans and technology. So we have to be the ones developing the models. And then once we validate those models and say that they're good surrogates for the real world, then we can then start doing the engineering that is more traditional to engineering. So that's kind of, where we sit in this kind of intersection there. So we care about what models are because we have to build them. So, what are models? And so I gave examples of fashion models, animal models, models from physics, like the Bohr model of an atom. And I was saying that the common thing among all of those models is that they answer what if questions. So if I ask you a question on an exam about what the definition of a model is, like this is what I'm looking for. This simple answer is anything that helps you answer a what if question. It doesn't have to be mathematical. It doesn't have to be computational. It could be anything. It could be a fashion model. It could be an animal that you hold in your hand. It could be a graph. It could be something that is just held in the mind, a mental model, a heuristic about the real world that helps you get through the world to make predictions about it. That itself is a model, even though it doesn't have a tangible form. So anything that helps you answer a what if question is a model. And what we're saying is that none of those models have to be perfect. It is not our goal to build perfect models. It's our goal to build models that help us move forward in the world. And as engineers, to build useful designs, to sort of, it gives us a way in to be able to start doing the work of engineering. So with that in mind, although the things we build become models, we learn a lot from them, especially when terrible things happen, when things we didn't expect happen, when failure modes happen that we didn't anticipate. We learn a lot from those. But when we're building artificial models, which hopefully prevent us from having to learn in catastrophic ways, sometimes to get generality, it's actually better for our models not to quite be as realistic. So some of those fine-grained details that are specific to one particular system, if you try to build them into your model, it might make your model a worse representation of all of the systems that you're being asked to come up with a solution for. So sometimes the best models are not the ones that are the most realistic, that have everything thrown in. It is sometimes okay. In fact, it's preferred to leave certain things out and only focus on the things that are the salient features of the problem. So what is the core problem at an airport that you need to solve when you're coming up with something to deal with the traffic going through the airport or the luggage going through the airport and so on? If you're talking about a shipping system or supply chain management or a factory, what are the core problems for the particular stakeholders that you are trying to build solutions for? And that might be the whole industry. And if you have to think about, well, what generalizes across the industry, there might be certain things that you occasionally need to turn on, like, well, there are a certain fraction of the industry does it this way, and a certain fraction of the industry does it this way, and maybe my model needs to be able to accommodate that. But if you end up building a model for this fraction of the industry, and then you end up making recommendations to this fraction of the industry, then they're going to be very upset when your recommendations don't hold because they are specific to these changes you made for this group over here. So sometimes we do have to get down, down deep. And if the problem is very specific, we need to build all that into our model. But if the problem is relatively generic, sometimes it's better to leave things out. So realism is sometimes a hindrance to good modeling. So it's not about how realistic, how precise your model is, it's how useful it is. And the utility of a model sometimes has as much to do with what you leave out than what you put in. So this is the type of stuff that we talk about this semester, combination of kind of math, stats, and programming all here in the middle. I would say it's definitely a lot more than programming. This isn't just a class where we teach you about Arena. I don't use Arena. I do a lot of modeling in my work, and my work as my researcher or my research and past work in industry. I never used Arena, and I still don't use Arena in my research work, but we use Arena as a teaching tool in this class. It is a tool that is used in industry. It's just not my tool of choice, but it has a lot of benefits for being used in a class like this. So I don't want to make you think that this is a class on Arena, the software program, but we are going to use it. So this class really is bigger than that. It's a class on the math stats combinations that complement that programming. So, we have to solve these challenges of how to build useful models and how to make those models useful and practical for you to use as an analyst and as an engineer. So our models have to be, once they run, they have to mean something to our stakeholders. And we actually have to be able to run them in a reasonable amount of time. And so, roughly speaking, this first bullet is the bullet that, is pre-midterm, and this second bullet is kind of post-midterm. And roughly speaking, so those two things are going to matter, and they're both going to require not only programming, but a decent amount of math and stats combined with that. So strong statistical methods are going to be a core foundation of this course. So that's kind of the idea. We combine all these things into 475. Each one of these, it's kind of going to be a survey of these things. If you're interested in any of these topics, you can drill down a lot deeper, and there are different avenues to do that. This is not meant to be, the whole iceberg. It's just the tip of the iceberg for stochastic simulation, but to give you sort of a way forward if you end up finding yourself doing this in future jobs and so on. So that's our recap of where we were. And now we're going to drill down today into simulation specifically. So we have a good background for what simulation models are and what terms do we need as we go into discrete event system simulation, which is the core simulation tool for this course. So before we do that, any questions about any of these foundations, modeling foundations? It makes sense so far. Okay. All right. So simulation modeling. So there are three, you can basically divide sim up into three major categories. We focus primarily on this one in the top right. The bottom, discrete event system simulation. There is another course in IEE, 477. Some people take as electives, a lot of engineering management students take. They focus on system dynamics modeling. So that's also a very popular modeling framework. You actually find courses at ASU in WP Carey that give you system dynamics modeling, as well as courses in school sustainability using the same tools that they teach in 477. And then there's agent-based modeling, which is more popular in the sort of biologists and social scientists. And so we're going to talk about all three of these and then come back ultimately to this one where we spend most of our time this semester. So talking about system dynamics modeling, and this is a core focus of 477. So we're not going to do any direct experiments with system dynamics modeling in this course. This is just meant to give you an idea of what the differences are between what we do in this course and what you might see in something like 477. These models are meant to model kind of coarse-grained, mile-high perspectives at systems. So they're not meant to model the day-to-day. Like if you're thinking about modeling an airport, it's not it's not meant to model, what happens on a minute by minute time scale for an airport. It's more meant to model what's happening with major trends across the seasons, for example, those sorts of things. So average behaviors. And so the focus here is on causal interdependencies. So usually the first thing you do with a system dynamics model is you say, what are all the components of the model and how does one component potentially influence another? And you map out this causal map, and then you build a diagram of how, well, if something changes away from the average, so if the average, I guess, perspective, if the average changes for one of these variables, all of the things that are causally connected to it, how might their average behavior change as well? And so you're modeling kind of a prediction about average behavior as it moves through these causal maps. That's what system dynamics modeling is all about there. These are very fast to simulate because we're modeling averages. So these are basically mathematical models that are, in some ways, they're very simplistic. So a system dynamics model can model a disease spread in a population, not by keeping track of every individual in a population, by keeping track of, well, we're going to say the population's got three types of individuals. There's individuals who are sick, there's individuals who have been sick and are now better, and there's individuals who have not been sick. And if you model, the population as those three groups, then you can say that, well, on average, if I have half the population that's sick and half the population that is not sick, then how quickly will the not sick part of the population get sick on average? Those are the types of mathematical questions that you try to answer with system dynamics modeling. But instead of writing them out as differential equations, you'll draw them into these diagrams, which are turned into math behind the scenes. So they're very fast to simulate because they don't have much detail. They're basically just a couple of differential equations. They have relatively few parameters for that reason. But the disadvantage is that because you're modeling averages, you can't answer questions like, will this person in the population be more likely to get sick than this person in the population? So in a system dynamics model, it's more about given the general risk to a population. So given that half the people in the population are sick, well, that means that for every person, roughly speaking, if they bump into someone else, half of the time it's going to be a sick person and the other half of the time it's not going to be a sick person. Now, so on average, you can say, what is the chance of things spreading? But if you actually talk about an individual person, they have their own, they might be embedded in a bunch of people who aren't sick. And so really, it's not realistic to say they have a 50-50 chance. On average, the average person's a 50-50 chance, but every individual person does not. So because of that, you lose out on a lot of the predictive capabilities you can get at the low level, at the individual scale. But you end up making predictions at a large scale very quickly. That's the kind of advantage, the trade-offs you get there. So these are what system dynamics models look like. This little video here, this is not modeling the way a disease spreads through a population, but it's modeling the way a product spreads through a population. This is a model, a famous model called the BAS model of innovation diffusion. So you've got populations split up into potential adopters and adopters. So these are people who bought the iPhone. These are people who could buy an iPhone but haven't already. And in between that, you have these new adopters, and that's a so-called flow. And so there's like a valve that will gradually turn potential adopters into adopters. And the rate of that flow, how much it's turned on, that valve, depends upon how many adopters are currently there and how many potential adopters are currently there. If there's no potential adopters left, the valve turns off. If it's all potential adopters and no adopters for them to observe, the valve is also close to being off. Roughly in the middle, where you've got a lot of potential adopters and a lot of adopters, there's lots of opportunities for the potential adopters to see the product. And so then you get a more rapid conversion of potential adopters to adopters. And so you get these graphs that are up here. So they talk about you've got the innovators and new. So you get sort of this peak and flow that happens roughly in the middle of the cycle before everything saturates. This is the type of analysis you do with a system dynamics model. Again, it's not talking about how likely you are to buy the product. It's saying on average, roughly speaking, what's the pattern going to look like as you move towards market saturation? That's a system dynamics model. From an airport perspective, if you're building one of these things, you might ask a domain expert, a subject domain expert, all of the things that might affect delay or might affect any dynamic process inside an airport. And you build one of these causal loop diagrams and you say, well, bad weather conditions, those affect delays, and air effect defects, those affect delays. And there can be feedbacks where delays may change standards, which may reduce airport defects, which may end up regulating the delays or reducing these delays. And so you throw all these things in, and it takes a long time for delays at an airport to affect standards to reduce those defects. So again, we're zooming out, and we're not thinking about what happens on a day-to-day for the airport. We're talking about what happens even from year to year. And so these models help us sort of say, if we were to put regulation in, how might we affect the industry to change over time? That's the type of thing. And once you have all these potential causal relationships, then you can build them into these flow diagrams, like the Bass model one I just talked about there, where you have stocks, which are like, number of potential adopters. They're a bucket that is full or empty. And then those buckets are interconnected by valves. Valves empty some buckets, and then they fill up other buckets. And they draw little valves here. So here's a valve, here's a bucket, here's a valve, here's a bucket, and so on. You then write the rules for how to crank that valve based on the average bucket height of all the other buckets in the system. And that's what all of these little lines are for here. And then you hit go. And what you're doing when you're hitting go is every valve is a dx dt. Every valve is a differential equation. So this is a system of differential equations. And so you're drawing out diagrammatically what you might write out in an ODE class, in a differential equation class. And so then you hit go, and behind the scenes, it builds the differential equation and it solves it numerically for you. So it sort of does the secant method, where instead of solving it symbolically, it draws little lines and it connects them and it draws graphs over time, so that it gives you these graphs of what might occur in your airport system. And you might get graphs that look like this. And so this is, again, modeling, and an industry level, like a macroscopic property over a long period of time. And here they said they've got these parameters. This was from a paper. And they said, well, what happens if you change these airport parameters by increasing them or by decreasing them or by leaving them the same? And then that's what these three lines are here. And so they talk about how these diverge over time. So apparently these parameters, when you increase them, it increases overall average delay at airports. And when you decrease them, it decreases overall average delay at airports. And so this is meant to make sense of the rat's nest that is here. That's what system dynamics modeling is if you trust causal relationships, what average behavior of the system do you get over long periods of time when you zoom out at a mile high? That's system dynamics modeling. So that's not the type of modeling we're going to do in this class, where we're going to zoom in a lot closer, but this is a different perspective. So there are other application areas where this is a very valuable perspective to take. It is, people don't care about the day-to-day. They do care about the long-term average trends. And that would be better, not for these models that we're going to build in this class, but for those models that we talk about in classes like 477. So different application area, different modeling. Not all modeling is used for the same problems. Okay, so that's system dynamics modeling. Any questions about SDM, system dynamics modeling? Again, not a core concept of this class. I just want you to know it exists. Okay. So then on the other side of that, there's agent-based modeling. It's often used by scientists, biologists, social scientists. In this case, it takes the complete opposite perspective, where we do model every individual in the system as a unique entity, as someone that we have to keep track of. It's not just an average anymore. So we focus on how they interact. So they're often very spatially explicit. So we are literally going to say there are 2,000 people in this airport, and we're going to put 2,000 little individuals in a virtual airport and let them roam. And whenever they bump into each other, we're going to define what happens. And whenever they bump into other parts of the airport, we're going to define what happens. And there's not going to be a strong mathematical basis behind it all, like not a differential equation behind it all. It's going to be bookkeeping whenever each one of these individuals bumps into each another individual and then changes aspects of those individuals. So because of that, it potentially can be very realistic because it looks like you're simulating a real world. It looks like a video game as you play these things through. The downside is that they're slower to simulate. There's a lot more to keep track of. And they can be just as difficult to understand as real systems because they look just as ugly as real systems. This is one of those examples where sometimes it's better to remove yourself from the system and look at the large scale patterns as opposed to trying to understand all these individuals. And then the other problem with that, it's very difficult to validate these models because you're there's so many different parameters. There's so many different ways you can change how one individual interacts with another individual that now you have to justify all of those choices. You could say, oh, well, when pilots bump into passengers at the airport, there's this interaction. And when flight attendants bump into people at the airport, there's this interaction. And you can say, well, why are those interactions not the same? Well, I just guessed that they weren't. So there's a lot more that you have to validate. You have to justify in all of these different choices. So they can be difficult to set and difficult to then justify to your stakeholders. But when you do that, you get a lot of opportunities to model different types of systems. So, again, this looks kind of cartoony, and part of that is just the visualization looks a little cartoony. But, it's this idea that you can model, whole complex city grids here. Now, because there's so many parameters here, they didn't put in, there's stoplights and cars, but that, there's only one type of car. So that's a simplification they had to make because, there may as well be one type of car because once you put multiple types of cars, you got to validate all the different behaviors of those one type. And that's just all kind of junk because you don't have that data anyway. They might as well just assume it's one type of car. But you can see that sometimes cars are in jams, sometimes cars are kind of off on their own. So you get diverse patterns that look relatively realistic when compared to system dynamics models where everything's smooth. They don't have to be moving vehicles. You can also simulate networks like this. So this was a model that pulled from a paper that was modeling demand response in power systems. So this is the idea that you set a price and a thermostat automatically then changes the temperature at the house in order to use less energy at that. And you want to kind of see how that works over time. So they simulated a neighborhood of houses that are connected to different generators, and then they allowed those houses to have different behaviors when you send price signals out to see overall what the patterns were in this neighborhood as you sent out these patterns, these prices. And then there can be, this is, I put this up here because I gave the example for system dynamics modeling of keeping track of the number of sick individuals, the number of infected individuals, and the number of individuals who've gone through the sickness who are now better. And so this is an alternative way to model disease spread, where rather than keeping track of those three boxes and saying, what's the average flow from one box to another, you just say there's 150 individuals in this population, and I'm going to let them move around randomly. And when they bump into each other, if they're sick, there's a probability that the other one gets sick. And I don't do any math about the counts ahead of time. I can do all the counting afterwards. And I just watch how the sickness flows through this kind of moving population here. So these are the types of things you get out of an agent-based model. I think I've got some videos here. So this is a kind of almost a sort of a silly example from an airport case where you might say, I noticed there's a certain distribution, and I'll play this in a second. There's a certain distribution of delays in an airport. Well, you can say, well, what would be a good baseline to say that I'm doing a good job. So what if we didn't have any queuing system and people just randomly arrived at the lanes and then push through the lanes based on when the lanes are on or off? What would the delay be there? And there may not be a clean way to model that just totally random, unstructured way of arriving. So instead, you do this empirical study. And so I think that's what was happening in here. So this kind of ugly thing where people are arriving, they're arriving to these lanes. This simulation model has the ability for you to turn on and off lanes as it's running. And you see people go through the lanes that are open. They don't go through the lanes that are closed, and it keeps track of how many passengers have gone through the system, how many passengers are currently work in progress in the metal detector, and you can do stats on these things. And you can say, like, well, does my fancy queuing system that I designed do any better than this, and what metrics? So sometimes these agent-based models, because they're so hard to validate, almost work better as baseline generators. So they help you simulate the kind of weird and artificial case that you need to say, I need to at least be able to do better than this case. And if I'm doing better than this case, then that's great. But if I am doing worse than this silly case here, then maybe I'm doing something wrong. So a lot of times, we're not using the agent-based models to do better designs, but we're using the agent-based models to give us a distribution of what would be expected if we didn't do a good design. So that's what I mean here. I think I've said sometimes they're better at generating null models. So they're generating sort of statistical distributions of what you'd expect if you didn't intervene intelligently. Okay. So questions on this example or so far agent-based modeling? Before we flipped, we will have one lab. We'll have you look at some agent-based models for a couple of different systems, so you have some experience working with them. They're relatively easy to work with. They came from a culture that was not a programming culture, so it was sort of how do you get non-quantitative modelers into the quantitative framework. So social scientists who didn't have the training for that wanted to still simulate complex social systems. Consequently, the tools for agent-based modeling that are out there are relatively easy to use compared to the ugliness that is Arena, for example. So it's really easy for us to spin these up and play with them, and that's what you'll do, I think, in Lab 4. Okay, so then that brings us to our focus here in 475, which is on discrete event system simulation, otherwise sometimes known as process-centric modeling. So we're going to draw diagrams that look like this. It's in between the two of what I just said. So the idea here is we do keep track of every individual in a system, but we don't give the individuals agency. In an agent-based model, there are rules you have to set for how that individual moves through an unconstrained space. I can walk anywhere, roughly anywhere in this room. And so if you want to model me with an agent-based model, then you have a lot of decisions to make about where I'm going to step next. But in a process-centric or discrete event system simulation model, we still keep track of there's an instructor and there's 70 students or whatever. But we come up with processes where it'd say, well, the instructor can only be in a certain number of places. They can be in the front of the room, the back of the room. Maybe that's all we're going to model in our system. And then we allow the processes to decide when to move the instructor back and forth, when to move the students. We visualize that in a way that makes it look like the instructor is an agent moving themselves around, but they're really more like a pinball in a pinball machine, or they're like a marble that is being moved from one compartment to another based on what the compartment wants. So this compartment says, now it's time for you to move from here to there. So in some ways, it's a little bit more like the system dynamics model where water is moving from one bucket to another, but it's like we're zooming in on the molecules of water. So now the buckets don't have fluids in them. They have these granular bits in them. They have actually a count of individuals in the buckets. And the connections between the buckets decide when the individuals move, not the individuals themselves. At a high level, that's a big difference here. So Individuals are passively moving through simplified descriptions of sequences of activities. That's the key difference here. So we model then how quickly individuals arrive at those locations. So if I'm modeling the classroom, I model on average, how often do people arrive to the door? Now I say on average, that's the modeling parameter. Like it might be that students arrive, you know, five, like they might arrive one per minute, coming into, we're talking about, coming into the class there. So on average, now we're going to randomly sample from a distribution that has that average. So they won't arrive purely at one per minute. Some will arrive, like there might be a cluster of five, and then there'll be one or two 3 minutes later, and then a cluster of 18 or whatever. But on average, they'll arrive one per minute. So we'll tell the simulation tool we want it to be drawn from an exponential distribution that has an average of one per minute. But then it will then draw randomly those arrivals. So we have to model how the distribution of arrivals as you move from the outside area to the inside area. We might model, the distribution of how long class durations take. We're modeling the time at which entities spend in every compartment. And those are the key modeling parameters. And then once those times are up, then the marbles get moved either in right from one bucket to a next, or they have random choices that to make. Like you could be that, you get 70 entities in this classroom, and then maybe 20 of them go to lunch after the class, and the other 50 go to the next class. And so that distribution of 20 to 50, that's something else that we have to model. So these are passive entities that get moved around by the system in random ways, and we model properties of that randomness. That's what we're doing here. So how long each resource spends and how individuals arrive. The advantage of this is that it is much more realistic than system dynamics modeling. We are modeling random variations at the individual level. We can say, on average, how long does this person arriving to the, sorry, not on average, I would say, we can say across individuals, what's the variation in time it takes for an individual at a bank to get service? We will be able to see across the distribution of individuals we simulated, some individuals got service quickly, other individuals had to wait 15, 20, 25 minutes. So we get that whole distribution out. So it's more realistic than system dynamics modeling. But because we don't give every entity agency, there's a lot less we have to model. So it's much faster than agent-based modeling. So it's a good fit to our engineered systems where we really expect certain things to have a flow. We expect customers to arrive, they go into a queue, they get serviced in an area, they go and sit down. We expect, factory parts, widgets to arrive at a factory, them to go one way or another, them to be processed, them to be reassembled. We have these diagrams of how things flow. We just don't know how long they stay at every one of these points. And that fits really well with this type of modeling. The downside is if you have state-of-the-art systems that are more, if you've got some sort of advanced chemical process where you just put a bunch of components into a vat and shake it up, and then they dynamically interact, and then suddenly you have widgets that self-assembled inside that vat of magic goo. Then that is something that if we need to simulate from a from a computational perspective, might be better fit as like an agent-based model, because there's no processes that are easy for us to model as sequences of events. And it requires a background in stochastic modeling. So as we're going to define a little later here, these parameters, like I already kind of hinted at it, like we're not just going to say there's 5 people per minute arriving at the door. We're going to say there's an exponential distribution with an average of 5 arriving at the door. So it requires us as modelers to use probabilistic distributions as our Lego bricks that we plug in together to build these models. And that requires a little bit more background from in probability and in stats. So it's a little more domain knowledge on your side, ends up making it much faster to simulate in the computer side. So that's kind of the overview. This is what some of our simplest models, like that you'll start building in, say, Lab 5. Process flows like this. Passengers arrive to security at a particular rate. It takes a certain amount of time for their document checker, their TDC, to check their documents. Some of them pass security and go on. The rest of them maybe have to get checked again or just get asked to leave. They can't, they're denied entry. Very simple model where we're going to have a number of entities in every box. You're going to say how many people are arriving right now, how many people are in line waiting to get checked, how many people passed, and how many people were rejected. Simple model like that, we can add more interesting visualizations to it. So this same model as it runs, we can put a little line up here where we've got a document checker that's always there. We're going to learn that we call that a resource. The things that are always there, the things you have to wait on, those are resources. And then the entities line up here at the end of this line waiting to get access to that resource. So this actually is starting to look like a overhead, like a good cartoon description of a real system. It will start looking like an agent-based model when behind the scenes, the logic looks like this flow chart. It's much sort of simpler. And then we can, the WIP, we can say how many people are currently in the system, how many people are with the document checker and in line, and we can plot that over time, and that will look like real data. So I've got, I think, a sim of this running. Here, we've actually gone so far as to create a 3D representation of the same data down here. So you can see individuals arriving at the system. So this is the same thing, but visualized in 3D. There's the document checker there. As the system runs, and I think this is going to speed up here. So I'm going to drag the speed here over to speed this thing up in just a second. And so it speeds up and you see people arrive and whatever. In this graph here, this starts looking like real WIP data, real, real information that you might see in a real system. But it's very simple to simulate. It's a very simple flow. What's making it look so realistic is that use of randomness. So we can have random arrivals, random variations in how long it takes to check your documents. And that's what you learn in this class. And also, I hope in classes like 470, is that the average behavior, those are just like, that's a rough idea of how you think your system's going to work. What really makes or breaks the system is what happens when there's bursts of traffic, or when happens, or how much costs you accumulate when there's no traffic and your resources are tied up not doing anything. So those variations, that's actually where the interesting engineering happens. And that's what this framework is doing, is it's allowing us to model those variations. And that's what we see coming out in these WIP data here. And this is Arena, this is Rockwell, and this is an older version. You're going to work with a slightly newer version, but these are the types of models that you build in Arena. Okay. So not spatially explicit, but we visualize it as being spatially explicit, and because it gives you a plausible idea. That's even, I think, better shown here. This is a Arena model of an emergency room, emergency department. So you've got cars that arrive, they drop off patients, and the patients go and visit with a receptionist. They wait in the lobby. Then they go and they wait in another waiting area. They go into beds. The beds are occupied. They clear the beds. The beds go through different states. So sometimes I don't think red is a good sign for this patient. So, they go through these different states and then eventually they depart. And then that frees up more space for these. So this here, it looks to me almost like an agent-based model. It looks like a realistic movement of not passengers, of patients through an emergency department. But if you think about it, it's still going through a sequence of steps that we would expect the emergency department to do. There's random variation in how quickly people arrive and how long it takes for them to get checked in, and how long it takes for them to wait. They're waiting on others. So there's randomness on like how long you need in a bed. That's random, but that is going to preempt someone else from using that bed. So then there's these interdependencies that are very difficult to predict the downstream implications for the whole system's performance. And that is what we're kind of capturing here. So it looks pretty realistic, but the underlying model is going to be very simple, but it generates these beautiful data sets that we can analyze. So this is the number of patients in the system. This is the type of patients. So critical, serious, fair, total number in. We've also can get total number out. We can see here the utilization of the beds. So, this might, we'll learn how to read these numbers, but this tells us here that, which resources were underutilized, were idle a lot of the times, and which resources were constantly in use. And so we're constantly being waited for. We get all of that data out here. So a lot of great looking, realistic looking data. And yet this is what the model looks like. When you're building the model, it's a relatively simple flow chart. I'm not showing you when you drill down into this secure a bed step here takes time. And that's going to have one of those random distributions where we're going to have to figure out how to parameterize that in a realistic way. What is the distribution of time it takes to secure a bed? What is the distribution of time it takes to wait for a doctor? And then there are going to be delays, which are those interactions between, one entity and another entity. So even though I'm ready for a doctor, I can't see a doctor because all the doctors are being used right now. And so we have to keep track of those delays, those extra delays. So, but overall, these two flow charts, I mean, this is from patient room, out of the patient rooms. This is from triage area, routing to bed or routing to the next stage. So it might be that this person from triage goes directly to an admitting, or they go to a bed. So there are options here, there are branches, but it's not that complex. I think relative to how rich that visualization looked, I'm kind of surprised that it's this simple behind the scenes. And so that's what we're going to learn. How do we build? And this makes it very easy to defend because we can now go to our stakeholders and say, I know you see this complex visualization, but do you have anything to argue with here? And your stakeholders can see that it's a relatively simple process. They can very quickly say, oh, you're missing a step, or no, that's it. You got it. And you didn't, go too far. You didn't add a bunch of extra steps. So it's easy to communicate, but it still allows for very rich behavior. That's discrete event system simulation. Okay. And we can elaborate on these models. Here's that original model I showed you from the document checker. We've now added downstream components. We've added an X-ray. We've added randoms checks and so on. So you can make them more and more elaborate over time. You can build on them. They're very flexible, easy to change, easy to study, and you get real data out here. So this is the waiting time at a particular queue. And not only are you getting average time, but you're getting confidence intervals. You're getting the whole distribution of time out, real world data with real variation. That's what we like in this class, that real world variation. Variation, you get utilizations, you even can get costs. You can say every time I use a resource, it costs a certain amount. Every minute the resource is idle, it costs me a certain amount. And at the end of the day, Arena automatically calculates those costs for you. So it can say that you made this much revenue, but you had to spend this much cost because your resources cost this much amount when you're using them and this much amount when they're sitting idle. And that will tell you if it's, maybe time to buy a new resource or sell some existing resources. All that's automatically calculated for you. You just have to parameterize them. You can use this in a wide range of industrial applications. Not just airports and emergency departments, factories for sure, and non-industrial applications. So this was a paper written now a little while ago, but it was about gleaning in this sort of it was a food bank that goes and collects these apples that were not fit to sell, but they were collecting them so they could donate them to those that were immediately in need. And so in order to figure out how to staff, because this would be like somebody calls you up and says, hey, I got a bunch of apples. If you don't pick them up now, I'm just going to chuck them. So you have to have this rapid response available. So how do you organize all these volunteers who are ready to do the gleaning with this need for the volunteers, which is random? And so they built an arena model to make this work. This is sort of the high level model. This is the implementation in Arena, and they use that to figure out how to properly staff. So a lot of different applications you can do with the types of models we're using. So that's a preview of where we're going. So any questions about the three modeling types or anything I brought up here? You're not supposed to understand it all just yet, but I want to give you an idea of, why we're doing this modeling type and not one of the others. Okay. All right. Oh yeah, clickers. So let's do one of these. If my clicker will start. Okay. Okay. All right. So I just started the 475 class. So I'll do I'm going to do a short answer. Oh, where did it go? Sorry about this. I'm hoping to remember all these positions. All right, so let's do a quick. All right, question is, in a short answer, what type of simulation is primarily used in this class? So I mentioned there's three types of simulation: agent-based modeling, ABM, discrete event system simulation, DES, or we've also talked about system dynamics modeling, SDM. So ABM, DES, or SDM, what modeling framework are we using primarily in this class? DES, SDM, or ABM? And you can write it all out if you'd like to. Just the letters, or we write it out. And for time, I'll leave that up while we move on to what's next. All right, so feel free to continue responding to that, but let's move on here. So for those who've looked ahead and have downloaded Arena, there is a student version that's free. It's a Windows only, unfortunately, but it does run under Parallels and other similar programs. We also have it available on the virtual labs, so that should be available at Porto. You can access that from Canvas. But if you might notice that if you have an older version of the textbook, and in some of the diagrams that I have, and definitely some of the lab materials, then you'll see that Arena looks more like this one in the back, but the more modern version of Arena looks like this one in the front. So as of Arena 16.1, they completely made an overhaul of the interface and where some things are located. All the same stuff is there, it's just found in a different place. So if you open up Arena, it looks like this. That's normal. It's just it was just an overhaul of this one that looked like what it is back here. So just keep in mind that there's information about installing Arena up here on Canvas. So if you go to the course information page, you can find a link about downloading Arena, which will tell you where to find it and will give you some tips on installing it, hopefully the smoothest way. All right, so moving forward here, I just want to cover some modeling terms. For those of you who've already done the first lab, have seen some of these, and if you're going to move on to the first homework, you'll need them for that homework as well. Okay, so I've already talked about some of these, but now we're just going to try to give some formal definitions. So I'm going to frequently talk about a system. So a discrete event system, for example, a system. It's a group of objects connected for a joint purpose. The big thing here is you have to define a boundary of the system. So, that is basically defining what's in the system and what's outside of the system. So all the stuff I've been talking about, sometimes you don't have to put everything in your model, everything in your system. It's only the stuff that's really important to the particular problem area. So deciding on that boundary can be very difficult. So as an example here, if I'm modeling a classroom, I only need to care about the number of students and the resources used in that classroom. But if I'm modeling a university, then I need to include a lot more at a high level, but maybe I leave out things that really only apply to classroom operations. Maybe if I'm modeling a university, I don't need to keep track of that little delay it took me to start iClicker. Maybe that doesn't affect things at the university scale. But at the university scale, I do need to keep track of the fact that there are a finite number of classrooms. At the classroom scale, I probably don't care that there are additional classrooms nearby because it doesn't really affect the dynamics of things here. Now I say that, this morning, another student almost followed me into the wrong classroom. So, that if I zoom out and say the delays in the instructor in getting to the classroom is sometimes affected by the presence of other things on campus. But there are probably other ways I can model that delay than saying like, oh, I'm going to put distracting classrooms there, and that's the best way for me to model the dynamics of what goes on in the classroom. I could probably wrap that up into just the distribution of time it takes Ted to get to the class. So you can leave stuff out of your model, and that's outside the boundary. You bring stuff in, that's stuff inside the boundary. Dynamical system, it's a system that can change over time. So you can just define a system. You can say the Earth is a system, and people say in the Earth, it's got water, it's got minerals, it's got all of these different components of the Earth. And then you could say in Mars has got a different set of components, and we can compare those two systems. But for that description, we don't care that much that the systems are changing over time. For most of our systems that we talked about in this class, the time component is critical. So we don't care that it's an airport. We care that it's an airport that's busy right now. And we care about how quickly does it go from busy to back down to not being busy. So changing over time, the system, the important components of the system are changing over time. In order to describe our dynamic systems, we're going to use the term state variable. A state variable is a bookkeeping tool to keep track of all of the things that can change. Like right now, a student just left the door, or just went out the door, and hopefully will be coming back. So I could keep track of the number of students in the classroom. That is a state variable, not the actual concrete number, 60. Like that is a state. So I could say, what's the state of the classroom right now? There's 60 students in it. What's the state variable? The state variable are the number of students in the classroom. So that's kind of the key difference there, is that state variable might be X, the state might be 61. So what is X? X is my state variable, the number of students in the classroom. What is the current state? 61. So that's a distinction there, state versus state variable. Now, these state variables change at certain events. At a random time in the future, that door will open and maybe a student will come in. At that event, when that door opens, the state variable changes. The number of students in the class goes up by 1. At that random time, that event, that's how we define events. Events are the key points in time that cause a state variable to change, or to cause, I should be more precise, to cause the state of the system to change. So discrete event system simulations, those discrete events, those are the things causing the state of the system to change. So that's what we mean by an event. An event is anything that causes some aspect of the system state to change. Now, or to have the opportunity to change. It might be that in a couple minutes, that door will open, and then it will close immediately because it's somebody for the next class and they thought the room might be empty. So there's an opportunity at that event for the system to change. Or it might be the door opens and somebody goes out and somebody comes back in, and simultaneously. So there is an event, the door opening is the event, and that gives the opportunity for the state to change, but it doesn't necessarily have to change. So that's what we mean by an event. We have different types of states. We have a discrete state variable that changes at only these event times. Now, you might say, There are other dynamical systems. So there, like the state just added by 3. So state plus 3 at that event of the door opening. So um, the now those types of that right there, that type of state, I'm referring to that as a discrete state variable. You might say, well, what about like a bucket of water? If I'm pouring water into it, it's constantly changing. So are there like an infinite number of events? And in that case, we give up on the event idea and we say, no, that's a different type of variable. That's a continuous state variable. So variables that can change smoothly over time, we're calling them continuous state variables. Variables that change only at those events, we call discrete state variables. In this class, we're only going to worry about discrete state variables, discrete event systems, systems where the state only changes on events, on countable moments of time. There are other types of modeling or more advanced versions of modeling in this class where you do worry about, like the temperature in this room. The temperature in this room is a continuous state variable. When it hits certain thresholds, then maybe it will change the likelihood of people staying to the end of class. So if it gets hot, then the exit rate of students from the class maybe goes up. And so maybe in some systems, I have to keep track of this continuous temperature variable that's moving continuously over time. But in most of our systems, we're not worried about that. And we're going to just assume that we can generate a model of events that characterize when things, the instant of time when things change. Things aren't continuously changing. Are there questions about those distinctions? A discrete event or a discrete event, a discrete state versus a continuous state, or the distinction between state and state variable. Okay, this is the first sort of example of something that this is where things start getting difficult definitionally, is all of these like weird, minor differences here. So as you do have questions, definitely voice them. If not in class, like feel free to send me a note or post something on Slack or discussion or whatever if you're not keeping these things track, because it's hard to keep track of at first, all of these almost insignificant seeming differences. All right, so now getting more down into it. Now, this is the stuff that you see on your homework and on the first lab. We have different types of things that we model. The first one in a discrete event system simulation is a resource. These are things that it's easy for me to say that they are just in the system all the time. Now, there are slight exceptions to that. So I would say a resource might be a document checker at the airport, somebody who you have to wait for in order to check your documents. Now, of course, that document checker at some time of the day is going to switch out and another document checker might switch in, or there might be 5 document checkers and they go down to 2. Now, I would say that you could say, oh, well, what happened to those document checkers? They left the system. They went home for work. And that's true. They leave the system. But we're not interested in the document checkers' experience. They themselves their primary focus is to slow down, is to do work that happens to slow down what we're going to refer to as the entities of the system. So even though document checkers, the number of them can change, they can themselves leave the system, whatever. Nominally speaking, most of the time, they are a static feature of that system. They are just always there, and you need access to them in order to move on. That's what a resource is. It is something that does work in the system. So document checkers, X-ray scanners, boarding pass kiosks, airplanes themselves, classrooms, seats in the classroom. If you come into the classroom and there's no seats available, you have to wait, and then you wait for someone to leave a seat before you can go into the seat. The seats are always in the classroom. The students are what's moving in and out of the classroom. Students have to wait on seats. Seats don't have to wait on students. So if it's a resource, it's not waiting on anyone. If it is being waited on, it's probably a resource. In contrast, entities. Those are the things that are waiting for resources. They enter the system, they would like to move through the system, but they can't immediately get through the system because they need access to a resource to get work done. They might need access to lots of resources to get work done. Eventually, they get all their work done, and usually they leave the system. So entities are the students that arrive at the class. Entities are the passengers that arrive at the airport. When an entity sits in line, waiting to get access to a resource, we call that a delay. And that is a very special duration of time. So that's going to be something we define explicitly too. Entities can have attributes. So somebody comes into the system and they have a certain amount of luggage. Somebody comes into the system, they have a certain background knowledge. They have a certain order that they want to make at a restaurant. Those things that, generally speaking, entities, students come through that door, but not every student is the same. So if you downstream are going to need to tailor the experience you provide that entity, you might need to stamp that entity with an attribute that allows you to differentiate them from other entities later on. So that's what we mean by attributes. And then getting to this thing up here, I talked about delay. There are two time durations. And this, I'm going to ask you to for activities on your homework assignment, but I'm not going to ask you for delays. And so you have to know the difference between them here. Both are time durations, but activity durations are predictable durations of service time at a resource. Delay durations are conditional waiting times having to do with how busy the system is. So the time you spent at a document checker, someone can look that up. There's a table of like, well, the average document checker takes 30 seconds to check a document. Sometimes it's 25, sometimes it's 35, but there's a distribution. I don't need to run a simulation. I know that ahead of time. And I use that knowledge to build my simulation. I then go into the simulation and say, this document checker on average, it's going to take around 30 seconds to delay the passengers going through it. What I don't know without running the simulation is how long you're going to wait in line for the document checker. So, you arrived at a document checker that's already checking someone else's documents, you wait in line. The time you spend in line in the queue, that is a delay. The time you spend with the document checker is an activity. So on your homework, I'm going to ask you for different systems to come up with different activities. So I'm not looking for the time it takes. Like I didn't ask you for a fast food restaurant, but if I did, I'd say, well, what's an activity versus a delay at a fast food restaurant? And I wouldn't want you to put down for an activity that the time it takes waiting in the drive-through lane is an activity. That's a delay. The time it takes when you hit the order window to give your order, that duration of time, it might take a minute, might take, some distribution of time around a minute. That's an activity. The time it takes for them to actually make your food once the order gets to someone who preps it, that's an activity. The time it takes for your order to get to a prep worker, that is a delay because they're probably going to take your order and they'll go on in the old days it'd be on a piece of paper. Now it's on some electronic queuing system. And so it goes into there and the person who's prepping the food doesn't even look at the next orders until they're done with the current order. So the time it takes for for it to sit in that list, that's a delay. So activities are the time that resources spend. Delays are the time that entities spend waiting on resources. Are there questions about that? That's like a key thing that's going to come up over and over and over again that I think usually students don't completely get locked in until right before the midterm. So this is a hard topic. So, if there are any questions about that or any need for clarifications, is it clear what I mean so far? Activity versus delay. Okay. That time that I just waited for that response, that's an activity. You can model, there's a distribution of time that people wait after they ask a question. And you can say whether that's a good distribution or a bad distribution. Now, if two of you raised your hand and I answered one question and the second person waited, the time it takes me to answer the first question is an activity. The time the second person is waiting to voice their question, that is a delay. Okay. All right, so inputs and outputs. Another way to view that, activities are inputs to our system, delays are the outputs of the system. We don't know the delays until we run the simulation. So we would like to know how long it takes for someone to get through a security line. We know how long it takes for someone to get through a document checker. We don't know how long it takes for them to actually get through the whole line. So the only way we know knowing if we make the document checkers faster, we likely will make the line move faster. But we don't know the impact of changing the document checkers time on the line until we run the sim. So the delay that we experience in the sim, that's actually what we as engineers are interested in. So the activities are what we know already. Those are inputs to the system, and we're going to call them input modeling. The term that we use in this class for figuring out what distributions to put in for activities is called input modeling. That's not my term. That's like the industry term. So activities are inputs, and then delays, that's what we study. Those are the outputs. Okay. All right, so I'm just going through this quickly here. Manufacturing system, that's kind of our breakdown. Parts, those parts have different features. Those features are attributes. Those parts, which are entities, cannot get through the system until they stop at different machines. So the machines are resources. The time they spend at each machine is an activity, but the time they spend waiting in line to get to the machine is a delay. I can go further here to say, all right, states and state variables. There's a state of the system, which is like whether a machine is busy or not. If it's not busy, it's a 0. If it's busy, it's a 1. So the state of the whole system is a string of zeros and ones. So if you have 5 machines, it's 5 zeros or ones. Now, whenever something arrives at a machine, then maybe it's 0 becomes a 1. Or maybe one of those machines fails. And so the state, there's like sort of a hidden state where it's either 0, 1, or X, where X is that machine is just not even available right now. So at any instant where you get a machine fails, a machine finishes its work, or a part arrives at a machine, those are opportunities for the machine to go from busy to idle, from idle to busy, or from either one of those to broken. And so any one of those instants of time we refer to as an event. So the state of a 5-machine system is this, 5 tuple. And so, then we can ask, why are some machines ever idle? You have 5 machines, why aren't you using them? And why aren't they always busy? Well, they might be downstream of other machines where they don't have access to parts until those other machines are done with them. So that's where we get into the complexities of this network of resources, is that you can have idle resources downstream, and the reason they're idle is because there's a bottlenecks upstream. So that's, what we do as operations researchers is moving the bottlenecks around. So are there ways for we to do things in parallel so that we can prevent these bottlenecks from causing a lot of these problems? So people are going to spend a lot of time waiting for their food at a restaurant. Maybe I can have them able to order their food from their phone so that they don't have to, we can use the time they spend waiting in line as not only time that they would normally spend just to order, we can actually use it as double duty as also time to make their food. So figuring out ways to stack delays or eliminate delays, that is the puzzle that we play in this class, or as industrial engineers, as operations researchers. And so that greatly relates to these types of systems. Other example, university, you might have entities that are students. They have lots of attributes associated with being a student. There's resources like classrooms and instructors. Generally speaking, you view those as the things that are always at a university. The enrollment at a university changes. Students are constantly coming into the university and then hopefully graduating and leaving the university. So they're coming in and out, they're flowing, they're like the water flowing through it. But the thing that the water's flowing over are the resources, the classrooms and the instructors. The inputs, what we already know, are the time it takes for the classes. The outputs, what we don't know, is how long the students will wait before entering the room. And so even though we know the distribution of the classes, we don't know how, how the distribution of, we might know how quickly it takes for a student to get from the dorms to the classroom. We might know how quickly it takes for a class to end. But when you have 79 students all are leaving their dorms at different times, taking slightly different times to get here, and you have a bunch of classrooms all over the university that all start and end at slightly different times, then it's hard to predict without running a sim how long people are going to wait to get into those classrooms. So that's why that's a delay, and we also view as an output. So we can model the states and the events this way. These are our state variables. The classroom is, and then the current states are either busy or idle. And I've given some of these examples already. All right, questions about any of that? Yep. Right. Well, sometimes we actually add attributes as people are moving through the system. So it may be if you go through, if you're modeling an airport and you get selected for secondary screening, or your entity, the entity in the sim gets selected for secondary screening, we might add an attribute that says they've already been screened. So when they go back through, we want them to skip the line. So tagging them with a flag to say this entity gets priority over these other entities is useful because that actually matches what's going to happen in real life. That if somebody comes through, they're going to say, you don't have to wait in that whole line again. We're going to cut you in front of this, and now you go through the X-ray machine again. So that's the usefulness of having dynamic attributes, which we usually do. The other, having attributes ahead of time is often a modeling choice because I could sometimes suggest two types of entities. So on your homework, so pro tip for your homework, I'm going to ask you for two types of entities per system. Now, you might say for a restaurant, there's customers as an entity. And you say, I can't think of another entity for a restaurant. And because I imagine attributes on a single customer that differentiate between mobile orders and in-person orders. Now I can get rid of the attributes and create two types of entities, mobile customers and in-person customers. And so now, so if you're having trouble on your homework thinking of two types of entities, try to think, is the entity you have in mind, can I subdivide it? And I might make the modeling decision to subdivide it into two types of entities, but for whatever reasons, the way I'm programming things up, it might make more sense for me to have one type of entity and then tag them with attributes and differentiate later. So it gives you some flexibility as a modeler. Does that help? Any other questions? All right, so I think so I'll touch up over this next time where we start, but this isn't as important for your homework, but these are the blocks we'll see, so we'll see that again. It's another example for that, and we'll start there. So I would normally do an eye clicker, but everybody's up, so I will hold off on that right now, and but we normally end with an eye clicker. So we'll see you on Tuesday. Uh-huh. Two different types of resources. Yep. It depends on what you're modeling. Like if you're modeling the time it takes for a waiter to go through, like they have to clock in, they have to get like, to change clothes or whatever. If you're trying to say like, we're trying to optimize how waiters enter the system, then they become the entities. But if you're modeling the experience of the customer, how do we make the restaurant work better for the customer? Then the waiters are an aspect of the customer experience. So I would say the waiters are probably resource. Yes. Yep. Mhm. Yes. Uh-huh. Yes, but then when you submit, just make sure that your responses, like in the lab, if it asks you to come up with examples, they should be you who should have examples, and the person you're working with should have different examples. Yeah, it happens, but try to add your own flourishes. And so, however, I mean, there's going to be sometimes there's the assignment's going to constrain that. If I ask you to solve for X, X can only be 5. So and I understand that, but when there is opportunity for these flourishes, then we would expect some deviation. And when we like, if we were to see like that, if you don't give us the benefit of like if there's no other explanation, like well, wow, this file, like binary, like this file is exactly the same binary as this file, has the same metadata or whatever, then at that point we'd say, well, you haven't given us evidence that, but if it's very clear, it's like, well, these two files are different files, and you sort of, it's like there are decisions that were made here that are how you decided to lay things out. Like then it gives us more evidence that, or just we need evidence that it is your understanding. So we just need to try to justify that to us. Mhm. You can, but then the labs are also flipped, and so you can watch them online. And so really the purpose of the in-person lab experience is for you to have access to the TA, to get clarifications, to work with them, and to work with each other whenever appropriate. But it's not meant to be another lecture. So it's if you don't, for this lab, if you don't think you need the in-person, you don't have to come to it. It's great for you to meet the TA though. Otherwise, if you do feel like you need to come in, if there's availability, sure, you can come to Tuesday or Thursday. Yep.
So I just saw what you said about first stuff that I asked about 4 foot 7,
Uh-huh.
and just came up with that question because just
Uh-huh. Yeah. You mean like create like, yeah, and sometimes you have to, if it's really necessary for you to study something that is tailored to a particular system, then absolutely you might say that I need to model the Las Vegas international airport differently than the Phoenix airport, because there's some, even though they're two desert airports, this one's got casinos in it and no other airport's got casinos in it. So I need to model this unique distractor to see and sometimes you might be saying, I want to see the effect of the casinos relative to all the other airports. So you might build a generic airport model, and then you add casinos to the generic airport model, and then now you've got the ability to see like how much extra business or how much less business do we predict a hypothetical Las Vegas airport without casinos, would make, or something like that.
Okay, that's it. So this so I just making them anything. So
Is something that's better, or
basic model just to go
well, as you'll
like yeah in this.
well, sometimes what you'll find is that it's really hard to build a high fidelity model that's super accurate. And so sometimes you say, well, I thought that this process mattered. Like this entity's experience got, delayed by this very rare event that wouldn't sometimes. So I need to sometimes it's possible that somebody's like, they might get sick, or maybe their dog will get sick or something like that. And you know that these things like that sometimes these things will affect some downstream parts of the system. And you have to say, or maybe a better example, you're modeling a store that's usually open 24/7. Now, normally, like, there are cases where rarely, like, something's going to happen and they're going to have to shut down, and then they'll have to spin back up again. And so there's going to be interesting processes that happen when they've when they've closed their doors and they reopen them, because normally they never have that reopening event. So you could say, I could build a system where I make sure that I give exactly the right predictions for this rare event, that when they have to shut down every once in a while and reopen, and I might have extremely precise results for that particular case. But all those other things you added, if they're not perfectly calibrated, may actually ruin the model from the nominal case, which is when it opens 24/7. So there's a lot more you got to get perfectly right, and there's a lot more opportunities to get wrong. Yeah. So in that case, they could say, this is a rare case, so I'm not going to build it into the model. And then that actually makes my model of the normal case better.
Okay.
Yep.
Yeah.
Okay.
When you mentioned about the
Mhm. Yeah, for this lab 1 and homework B1, there's a lot of overlap. That won't normally be the case. Mhm. Yep. Okay, well, let me go ahead and stop the recording here, especially because the sound's. Yeah, just